So in this lecture, I'll be covering about the concept of AVL tree deletion. So far, when concerned about the AVL tree insertion part, we have learned about the AVL tree insertion in the previous video. So coming to the AVL tree, it is also the property of the binary search tree. It involves the property of the binary search tree, and whatever the property that remains in the binary search tree should also be included in the AVL tree. That is, nodes that you place towards to the left subtree should be less than this kind of the root node, and whatever the nodes that you keep towards to the right should be greater than the root node. This property has to be involved even in the AVL tree. And coming to the next property, that is the balance factor. So within the case of the balance factor, that is the first property is of it is the binary search tree property has to be involved, and the next one, that is balance factor, has to be maintained. That is what we have said about the self-balancing tree. So self-balancing tree is whenever you are inserting the new node, or whenever you are deleting an existing node. In such cases, if the tree is unbalanced, then the tree has to be balanced. And in order to convert this unbalanced tree to the balanced tree, we have seen the various kinds of the rotations. That is, the rotations which includes, that is single rotation, and the next one, that is double rotations. And within the single rotation, we have seen about LL rotation and as well as RR rotation. And within the double rotation, that is which involves LR rotation, and the next one, that is RL rotations. So here the main objective of the rotation involved in the AVL trees is to convert the unbalanced state to the balanced state, because by inserting the new node or by deleting the existing node, there may be the balance factor may be beyond the range. The allowable range of the balance factor is, that is, it can be either -1, or it can be either 0, or it can be 1. And if by inserting any new node in the AVL tree, if the balance factor exceeds, that is, if the balance factor is beyond this kind of the allowable values, in such case, we can say it is an unbalanced state. And this unbalanced tree has to be converted into the balanced tree. That is what the rotations are being involved. So when to perform the LL rotation? The LL rotation is to be performed when the right tree is heavy. When the right tree is heavy, then you have to rotate left. And when to perform the RR rotation? That is when the left tree is heavy, then you have to perform rotate right. That is about the single rotations. And considering about the double rotations, that is LR rotation. So when you need to perform the LR rotation, that is when left tree is heavy, and out of which the right subtree is heavy. In such case, you have to perform the LR rotation. Similarly, when to perform the RL rotation? When the right tree is heavy, and out of which the left subtree is heavy. In such cases, you have to perform the RL rotations. So based upon this kind of introduction related to the AVL tree deletion, we shall cover about the AVL tree deletion part. So deletion in the AVL tree is similar to the deletion of the binary search tree. So if you need to know about the AVL tree deletion, you should also have the prerequisite to understand about how we can delete the node within the BST, that is binary search tree. So there are three cases involved whenever you want to delete a node in the binary search tree. The case one, deleting a node which is the leaf node. The second one, whenever you want to delete a node and this node is the only child, whether it may be the left child or whether it may be the right child. And the case three, that is deleting a node with the two children. That is a particular parent contains the two children, and if you want to delete this parent node, then that is what we can say about the case 3 scenario. So in AVL tree, after deleting a node, balance should be checked. That is what I've said about the rotation part. Whenever you are inserting the new node within the AVL tree, or if you want to delete a node within the AVL tree, and due to this operation, it may be the insertion operation or it may be the deletion operation, if the tree is unbalanced, that is a particular node's balance factor is out of this range, then in such cases you have to transform or you have to convert this kind of the unbalanced tree to the balanced tree by using the rotations which we have discussed. So coming to the case one of your binary search tree, that is deleting a node which is the leaf node. What does it mean? That is, here consider the AVL tree in this kind of the, this is an example of your the AVL tree. Of course, the node values has to be entered. So I'm focusing on the deleting the node with the leaf node. So this becomes the leaf node. Similarly, the leaf node we can delete. This is one kind of the scenario that belongs to the case one. And coming to the case 2, that is deleting a node with only one child. So here you can observe when deleting a node with only one child. So here if you consider this kind of the node, so this node contains only one child. Similarly, in the other scenario, consider there is a right child that is being present. Then this node, by deleting, it can be related to the case 2, because we are deleting a node. This is the node that you want to delete, which contains only one child. It may be either left child or it may be either the right child. And deleting a node with the two children. That is, here you can observe if you want to delete something like this kind of the node, which contains the two children. Then in such cases, this is related to the case 3 scenario. Similarly, here also if you consider this kind of the root node which contains the two children, that is related to deleting the node with the two children. So in AVL tree, after deleting a node, the balance factor should be checked. If the balance factor is out of the range, then you have to perform the rotations. What kind of the rotation is been involved? It depends upon the scenario or it depends upon the affected node. As we have discussed in your previous part, that is, what is this affected node? Whenever a node, by adding the new node or by deleting a certain kind of the node, if the balance factor of a node gets changed, it is beyond the range, then in such cases, that is the affected node. Look from that kind of the perspective and then observe how the tree looks like. So if the affected node, from the affected node perspective, if the tree is right heavy, then you have to perform left rotate. Similarly, from the affected node perspective, if you look at like the node, the tree, which is left heavy, then you need to rotate right. In the same fashion, when to perform the double rotations, that is, if the left is heavy, out of which the right is heavy, then in such cases, you have to perform the LR rotation, that is double rotation. And if the right T is heavy, that is, if the right tree is heavy, and out of which the left subtree is heavy, in such case, you have to perform RL rotation, that is double rotation. So consider the case 1 example. That is, here you are being provided with certain kind of the AVL tree, and the first prerequisite is you have to check whether the given tree is AVL tree or not. How to search whether the given input is the AVL tree or not. So the two properties, that is, it should be the properties of the binary search tree remains the same thing, and the balance factor has to be checked. So take any kind of the node, like take for example node 3. So node 3, which is being placed as the right child of node 2, that is correct. And observe the root node. How did I explain about the the binary search tree? Whatever the nodes that you keep towards to the left should be less than the root node, and whatever the nodes that you place towards to the right should be greater than the root node. So here, if you consider about the node 3 is less than the root node, but it is being placed as an right node, right child of the node 2. That is satisfied. Similarly, take any kind of the node like your node 6. Node 6 compare with the root node, it is greater. So the node 6 is greater than the node 4. That is how it is being placed as the right child. So the properties of the binary search tree is being satisfied. And the next one, that is balance factor. So by just looking at this kind of the AVL tree, we can say the balance factor is being maintained. It is within the allowable range. That is, balance factor of 1 is equal to 0, because balance factor of the leaf nodes will be equal to 0, because there is no left subtree and there are no right subtrees for the leaf nodes. Hence, node 1, the balance factor is 0. Node 3, the balance factor is 0. Node 6, the balance factor is 0. And coming to the node 2, that is when considered about the node 2, the balance factor, that is height of the left subtree minus height of the right subtree. The left subtree's height is 1. The right subtree's height will be equal to 1. So 1 minus 1, that will be equal to 0. And node 5's balance factor, that is height of the left subtree, that is 0, because node 5 does not contain any left subtree. And how about the right subtree? The height is equal to 1. So 0 minus 1, that will be equal to minus 1. And coming to the next part, that is node 4. So within the case of the node 4, the balance factor. So what is the balance factor of the node 4? The height of the left subtree, which is equal to 2, and the height of the right subtree, which is equal to 2. So 2 minus 2, that will be equal to 0. So this is how we can say it is an AVL tree. It satisfies the property of the binary search tree, and it also satisfies the property of the balance factor, where the possible values are -1, 0, 1. And consider you need to delete node 1. So if you recall about the AVL tree deletion, it is also quite similar to the BST deletion, that is binary search tree deletion. And there are 3 cases which are being involved. That is case 1, deleting the leaf node. Case 2, deleting the node with only 1 child. Case 3, deleting a node which contains 2 children. So if you need to delete, like according to this example, you need to delete the node 1. Observe this scenario, which case that kind of the node belongs to. That is, it belongs to the case 1. And what is this case 1? That is deleting the leaf node. This is your leaf node. So whenever you want to delete the leaf node, if you recall about the property of the binary search tree. So within the binary search tree, and if you are involved in the case 1, that is deleting the leaf node, directly you can delete the leaf node because it does not contain any left subtrees and simply the right subtrees. So you can delete the leaf node and then make that kind of the parent's left child to be equal to null. Or if the leaf node is right child, then make the parent's right child as null. So that is related to the case 1. And coming to the case 2, that is deleting a node which contains only 1 child. Deleting the node which contains only 1 child. That is, take for example node 6. So whenever you are deleting the node 6, here there is only 1 child that is been present. Then in such cases, make a link between the parent and the child. What does it mean? That is, consider there is some node that is being present, and similarly here there are certain nodes which are being present in the leaf node. And if you want to delete this kind of the node, observe to which particular case it belongs to. So it belongs to the case 2. Case 2. What does this case 2 says? Deleting a node with only 1 child. This node contains only 1 child. So I have explained whenever related to the case 2, such that make a link between the parent and similarly the child, and then remove this kind of the node. So by deleting this kind of the node, establish a link between the parent and similarly the child. That is what related to the case 2. And coming to the case 3. So within the case of the case 3, it involves such that, like, for example, if you need to delete this kind of the node which contains the 2 children, and observe what is the left subtree and what is the right subtree. So within your left subtree, you can take the maximum value that is been present in the left subtree or the minimum value within the case of the subtree. That will be discussed in your case 3 part. So far here, according to this kind of the example, that is you need to delete the node which contains which is the leaf node, that is case 1. And coming to the case 1, that is you can delete the nodes which belongs to the leaf nodes like node 1, node 3, and as well as the node 6. So node 1 can be deleted, which is the leaf node, and directly we can delete that kind of the leaf node and make the parent either the left child or the right child, depending upon the node that you want to delete, to be equal to null. So upon deletion this kind of the leaf node, observe how the balance factor remains. That is, balance factor of 6 is 0, balance factor of 3 equal to 0, balance factor of 5 equal to 0 minus 1, that will be equal to minus 1, balance factor of 2 equal to 0 minus 1, that will be equal to minus 1, and the balance factor of the node 4 equal to 2 minus 2, that will be equal to 0. So that is how we can say this is an AVL tree. No further modifications, no rotations are being required to convert, to transform into the AVL tree, because by itself it is an AVL tree. It satisfies the property of the binary search tree, and it also satisfies the possible values of the balance factor, and that is how we can say it is the AVL tree. No rotations are being required. Now consider the scenario, that is where we have, that is this is a node that is being present, AVL tree that is being present, 46, 20, and similarly 18, 54, 60. Find the balance factor, check whether it is an AVL tree or not. So the nodes that are being kept towards to the left are less than this root node, and the nodes that you keep towards to the right is greater than the root node. And you can also cross verify within the case of the subtrees. And the other thing is the balance factor. The balance factor of 18 is equal to 0, balance factor of 60 equal to 0, balance factor of 20 equal to 1 minus 0, 1, balance factor of 54 equal to 0 minus 1, that is minus 1, balance factor of node 46 equal to, that is height of your the left subtree, that is 2, minus height of your the right subtree, that is equal to 2. So 2 minus 2, that will be equal to 0. So it is an AVL tree. And what is the question that has been asked? You need to delete the node 60. Observe how the node 60 is been involved, whether it is the leaf node or whether it is the node which contains only one child, or whether it is the node which contains 2 children, depending upon the case. So this is an example of the case 1. So by deleting the node 1, that is node 60. So when you want to delete the node 60, observe, in continuation, if you are adding some other nodes like 18 and similarly node 7 are being added, consider. Then in such cases, identify whether the it is allowable balance factor is present or not. So node 7, 0, and so on. So the property of the balance factor remains. That is, take any node within this AVL tree, the balance factor will be within the range. That is, it may be either -1, 0, or 1. And whenever you want to delete the node 60, then in such cases, how did I explain about the case 1 scenario? That is, if you want to delete the node 60, you can delete, because it is only the leaf node. Leaf nodes can be deleted directly, and make the parents, depending upon whether it is a left child or the right child, to be equal to null. So in such cases, when you are deleting this node 60, so when here you can observe towards to the right, the node 60 has been deleted. But how about the balance factor? The balance factor of the node 7 is equal to 0. Balance factor of your the node 18 equal to 1, because 1 minus 0. Node 23, it is a leaf node, the balance factor will be equal to 0. Node 20, the balance factor will be equal to 2 minus 1, that will be equal to 1. The balance factor of 54 will be equal to 0, because it is a leaf node. And when considered about the node 46, So node 46, what is the balance factor? That is height of your the left subtree, that is 3, minus height of your the right subtree, that is 3 minus 1, that will be equal to 2. And this is where the node is being affected. So what is the node that is being affected? The node that has been affected is node 46. Look from that perspective, from this perspective, and identify whether it is left heavy or right heavy or so on. So if you look at from the node 46, you can observe the left is heavy. Left is heavy. And when to perform, you are aware about the single rotations and similarly the double rotations. So the first thing that you have to check is whether left is heavy or right is heavy. So according to this scenario, left is heavy. And also verify whether within your left tree, right subtree is heavy. Right subtree is not heavy. And that is how we need to perform the single rotation. And when it is left heavy, then you have to perform rotate right. And when it is right heavy, then you have to perform rotate left. That is what I've explained about the single rotations and as well as the double rotations. So according to this kind of the example, left is heavy. So when left is heavy, then you have to perform rotate right. That is single rotation. How to rotate right? Just make this kind of the 46. So node 20 becomes the root node and the right child becomes the 46. So when you are performing the right rotation, 20 becomes the root node and the right child will be, that is 46. And similarly, here you can also observe that the node 20 is right child. Node 20 is right child. Now becomes the left child of the node 46, the affected node. And the remaining values will be the same thing. That is node 54, which is being placed as the node 46 right child. And check the balance factor at every kind of the node. So the balance factor of the nodes it will be within the range. It may be either -1 or 0 or 1. That is how we can say this is an AVL tree. And consider the case 2. So within the case of the case 2, given certain kind of the AVL tree, check whether it is an AVL tree or not by two properties, that is BST and similarly the balance factor. And if you want to delete the node with the value to be equal to 2. So if you look at this kind of the node 2, you can observe there is only one child. That is node 2 contains node 3 as the right child. So this belongs to the case 2. So when it is a case 2, how did I explain about the case 2 scenario? If you want to delete the node 2, then establish a link between the parent and similarly the child. If you consider the node 2, the parent is node 4, the child is node 3. So establish a link between the parent and the child and check whether the properties of the AVL tree is being satisfied. So when you are deleting the node 2, or we can say like your grandparent and similarly to child. So consider this is your parent and this is a child and this is your grandparent. Then in such cases, establish a link from the grandparent to the child. So we are linking 4 and 3. And check the properties of the AVL tree. So it is the property of the binary search tree has been satisfied. And coming to the balance factor, that is balance factor of node 6 is equal to 0, node 5 equal to -1, node 3 equal to 0, and node 4 equal to -1. So the property of the AVL tree is been satisfied. In the same fashion, if you want to delete the node 12, so if you look at this kind of the node 12, so if you look at this kind of the node 12, it contains only one child. So if you want to delete this kind of the node which contains only one child, then in such cases, establish a link between the grandparent and child. That is node 20 has been connected to node 8. And the remaining nodes are being included in the same fashion. That is node 24 has been attached to node 20 and so on. And check the balance factor of, definitely we can say, this is not an AVL tree. That is node 40, 0, node 26 balance factor is 0, node 30 balance factor equal to 0, node 21 B equal to 0, node 24 B equal to -1, and coming to the node 20, that is -2. So if you look at this kind of the perspective, from the node 20's perspective, whether it is right heavy or left heavy, we can say it is right heavy. So if it is right heavy, then you have to perform left rotate. So you have to perform the left rotation. So when you perform the left rotation, then 24 becomes the root node And similarly, to the 24, node 20 has been attached and node 8 has been attached. And coming to the parents left tree subtree that has been present, then it has been attached to the grandparents right subtree. That is, here you can observe, that is for 24, that is 21 has been present, and this 21 has to be connected to the node 20 right child, and that is what the case 2 has been involved. And check the balance factor and as well as the property of the AVL tree. The property has been satisfied. Similarly, when you delete a node 30 which contains only one child, establish link between 20 and 25 and check the balance factor. So the node that has been affected is equal to, that is 20, because the balance factor of node 20 will be equal to 2. And the tree is left heavy, out of which the right subtree is heavy. That is, if you look at from the node 20's perspective, that is left is heavy, out of which the right subtree is heavy. Then in such cases, you have to perform the LR rotations. So when you are performing the LR rotation, I have explained the same scenario, like C becomes the root in the previous video. C is the root, and similarly grandparent is the right child of C, P is the left child of C, C is right tree if it is present, it is connected to the GP's left tree, and C's left tree if it is present, then it is connected to the P's right tree. And that is how you get the final AVL tree with the root node to be equal to 15. And coming to the node 3, that is here node to be deleted. Like take for example, given Sarankan of the AVL tree, and you have to delete, that is node 3. Observe the how does this node 3 belongs to, whether it belongs to the case 1 or case 2 or case 3. If you are concerning with the case 1, that is deleting the node with only one, it is a leaf node. And similarly, when concerned about the case 3, that is which contains 2 children. So node 3 contains 2 children, that is node 1 and similarly node 4. So in such cases, either you can find the largest value in the left subtree, or you can find the smallest in the right subtree. That is, if you consider node 15, assume node 15 has to be deleted. What is the largest in the left subtree? The largest in the left subtree is 9. So this value has to be replaced with the 15. And in the other scenario, take for example, if you need to delete something like your node 5. So within your node 5, what is the largest in your left subtree? Largest in your left subtree is equal to 4. So 4 should be replaced with the root node. Or if you also take in the other kind of the solution, what is the smallest in the right subtree? The smallest within your right subtree is equal to 6. So replace 5 with 6. That is what the case 3 is been involved. So node, if you need to delete this kind of the node 3, then find either the largest in your left subtree or the smallest in your right subtree. Not both the case. Either you can take the largest in your left subtree or the smallest in your right subtree. Replace the node with the root node or the node that has to be deleted. Then find whether the property of the AVL tree satisfies. If it satisfies, then it is okay. And also check whether the balance factor. So after transformation, what is the balance factor of each kind of node? If the balance factor is within the possible allowable values, then in such cases, that is the AVL tree. And coming to the AVL trees which have been implemented, what are the applications? So what are the applications of the AVL tree? AVL tree has its applications. That is, AVL trees are commonly used to implement dictionaries or associate arrays where the data is being stored in the key value pairs. And it is used in the applications that required improved searching apart from the database applications. In such cases, AVL tree has been implemented. And AVL tree also has its application when concerned about AVL tree can be used for indexing purpose, and they provide efficient retrieval of records based on the keys, ensuring that the operations like searching for the specific record or the range queries are performed with the optimal time complexity. So those are the applications of the AVL tree. To summarize this lecture, that is, we have learned about the AVL tree insertion, that is AVL tree insertion, single rotation and the double rotations, which are being denoted by LL rotation, RR rotation, and the double rotations, which are denoted by LR rotations and as well as the RL rotations. And when concerned about the insertion part, whenever you are adding a new node to the existing AVL tree, then check whether this can affect the AVL tree, whether all the nodes satisfies the property of the balance factor. That is, the allowable values are -1, 0, 1. And if it satisfies, then it is an AVL tree. And due to this addition, due to this inserting the new node into the AVL tree, if the tree is unbalanced, then in such cases, you have to do the rotations. Similarly, we have learned about the AVL tree deletion, and within the AVL tree deletion, there are three cases are being involved. Case 1, deleting the leaf node. Case 2, deleting the node with only one child. Case 3, deleting the node which contains two children. And similarly, after deleting that kind of the respective node and replaced with the respective, the node depending upon the case 2 and similarly the case 3, then find the balance factor of every node. If the balance factor is beyond the possible values, then perform the rotation depending upon how the tree looks like.